Hello, and welcome to our lesson on special sequences. Today we're going to explore some intriguing types of sequence, which you may or may not have seen before. In this lesson, we'll delve into different kinds of special sequence, such as the Fibonacci sequence, and examine their various uses. We'll also run through some practical examples to see how this new knowledge can be applied in different scenarios. So far, we've established a solid foundation by discussing arithmetic sequences which increase or decrease by a constant difference, and geometric sequences that increase or decrease by a constant ratio. With this foundation, we can now introduce new mathematical techniques by exploring special sequences. So let's get started. Let's dive into these special sequences to understand their unique patterns and applications. The first special sequence we will focus on will be the cube numbers. We previously explored sequences involving square numbers where each term is the square of its position. Cube numbers follow a similar concept, but instead of squaring the position number, we cube it. This means multiplying the position number by itself twice. For example, the first term is 1 to the power of 3. This is equal to 1. The second term is 2 to the power of 3, which is equal to 8. The third term is 3 to the power of 3, which is 27. And the fourth term is 4 to the power of 3, which is 64. Then the pattern continues. This sequence can be represented by the formula. The term is n to the power of 3, where n is the position number in the sequence. Recall that quadratic sequences had a constant second difference. Similarly, cubic sequences have a constant third difference. But what does this mean? Well, the first difference is the difference between each term in the sequence. We can see that the first difference is getting bigger the further into the sequence we go. The second difference is the difference between each of the first difference terms. Again, we can see that this is increasing as we go further into the sequence. But when we calculate the third difference, we see that this is a constant of 6. This is because we have a cubic sequence, which always has a constant third difference. This pattern continues for higher powers. For example, quartic sequences that have an n term to the power of 4 have a constant fourth difference. The second special sequence we will focus on will be triangular numbers. Triangular numbers are best understood visually. Imagine dots forming an equilateral triangle. To find the next term, you add another row of dots to the triangle. Here are the first 5 triangular numbers. The first triangular number is 1, shown as a single dot. The second is 3, a triangle with 2 rows, the first row having 1 dot and the second having 2. The third is 6, a triangle with 3 rows calculated by 1 plus 2 plus 3. The fourth is 10, adding a fourth row, 1 plus 2 plus 3 plus 4. The fifth is 15, adding a fifth row, 1 plus 2 plus 3 plus 4 plus 5. Algebraically, you can see that with each new term, you add an extra number. This extra number increases by 1 each time. Let's see if we can represent this with a formula. Notice that to find the nth term of the sequence, we add n to the previous term. For example, to figure out the fifth term of the triangle number sequence, we added 5 to the previous term, which was 1 plus 2 plus 3 plus 4, 10. Algebraically, this is the term-to-term rule. The nth term is equal to a multiplied by n minus 1 plus n. Interestingly, this sequence is actually a quadratic sequence. Try to see if you can work out the formula for the nth term yourself. The third and final special sequence we will focus on is the Fibonacci sequence. You will remember the Fibonacci sequence from the Extension Knowledge section of our Introduction to Statistics video. If you don't recall the Fibonacci sequence introduction, feel free to go ahead and watch back that video before continuing. The Fibonacci sequence is defined by the rule that each term is the sum of the 2 preceding ones. Let's see how it goes. The first term is 1. The second term is 1 plus 0, which equals 1. The third term is 1 plus 1, which equals 2. The fourth term is 1 plus 2, which equals 3. The fifth term is 2 plus 3, which equals 5. The sixth term is 3 plus 5, which equals 8. And it continues like this. If you have some paper, try continuing this sequence yourself. The Fibonacci sequence is all around us in many ways, such as the arrangement of seeds in a sunflower, the branches of trees, and even the arrangement of leaves on a stem. By recognizing these sequences, we can see patterns and make predictions in areas ranging from architecture to biology. That covers the main idea of today's special sequences. Now let's dive in with a real-world application. Let's attempt a problem that illustrates a real-world application for special sequences. Suppose you're an architect who needs to design a building that aesthetically resonates with nature's patterns. For this, you plan to incorporate the Fibonacci sequence in your design. Let's see how you can go about it. Imagine on your screen a blank canvas representing the floor plan of your building. Let's start by marking a square on this canvas. We'll call the length of this square 1 unit and the width also 1 unit. Next, let's draw a square adjacent to this with dimensions equal to the longest side of the square. Again, this will be 1 unit by 1 unit. Now we have 2 squares with side lengths 1 unit each. Here's where we see the magic of the Fibonacci sequence manifest itself. We can add another square whose side length is the sum of the last 2 squares' side lengths. That's 2 units. This new square's sides measure 2 units each. Continuing this process, we add another square to the design with a side length of the sum of the last 2 squares' side lengths. 1 unit plus 2 units equals 3 units. Just by doing this, we've now got the first 4 Fibonacci numbers: 1, 1, 2, and 3. You can keep on adding squares to the design following this pattern, each new square's side length being the sum of the previous 2. This will generate a series of squares whose side lengths form the Fibonacci sequence. The pattern as a whole tends to form a spiral known as the golden spiral, commonly found in nature. Revisit our lesson called Introducing Sequences to explore more detail about the Fibonacci sequence. Now imagine if each of these squares was a functional area in your building, for example, a garden, a common area, or a set of rooms. This would result in a Fibonacci patterned architectural design, resonating with nature and aesthetics. This is just one simple example of how the Fibonacci sequence can be applied in real-life scenarios. In today's lesson, we explored various special sequences. We focused on their unique patterns and real-life applications. We began by discussing cube numbers, where each term is the cube of its position number, such as 1, 8, 27, and 64. Next, we examined triangular numbers, which visually represent dots forming equilateral triangles, with terms like 1, 3, 6, 10, and 15. We then delved into the fascinating Fibonacci sequence, where each term is the sum of the 2 preceding ones, starting with 1, 1, 2, 3, 5, and 8. By recognizing and applying these sequences, we can identify patterns and make predictions. This lesson has expanded our mathematical toolkit, enabling us to see the beauty and utility of special sequences in everyday life. Watch the rest of the GCSE Maths course at Sophos Education.